Picture this: a cosmic enigma so strange it flips everything we know about black holes on its head. While black holes pull everything into their endless darkness, what if there were cosmic twins doing the exact opposite? Exploding matter and energy outward with unimaginable force. These are white holes, theoretical, mysterious, and possibly the key to understanding the birth of our universe itself. Some scientists believe the Big Bang was nothing less than a colossal white hole erupting into existence. And if that's true, these cosmic anomalies could be gateways to entirely new universes. Today, we're diving into one of the most mind-bending ideas in physics. Forget what you think you know about space and time. By the end of this journey, you'll see the universe in a way that challenges reality itself. Strap in, this is about to get wild. Let's break this down in a way that makes sense. Imagine a black hole as a cosmic vacuum cleaner, sucking in everything that comes too close. Now flip that image upside down. A white hole is like a cosmic fire hose, violently spewing out matter and energy instead of pulling it in. It's the exact opposite of a black hole, but just as mind-bending. According to Einstein's field equations, which describe how gravity works in our universe, white holes aren't just science fiction. They're mathematically possible, even if we've never observed one. Think of a black hole's event horizon as a one-way street. Once you cross it, there's no turning back. A white hole's event horizon, on the other hand, is like a no-entry zone. Nothing can get in, but everything inside gets blasted outward. That means if a white hole exists, it would be like a cosmic fountain, spraying particles and light with unimaginable force. Some scientists even suggest that a white hole could be the aftermath of a black hole, like a rebound in space-time where all that swallowed matter gets spat back out. Now, here's where things get even weirder. Black holes are born when massive stars collapse under their own gravity. But what creates a white hole? The math suggests it might be a singularity, just like in a black hole, but instead of collapsing inward, it expands outward in a violent eruption. Picture a balloon inflating at an impossible speed, except instead of air, it's space, time, and matter exploding into existence. Einstein's equations don't rule out white holes, but they do make them seem unstable. If a white hole were to form, it might only last for a fraction of a second before vanishing. That could be why we've never detected one. Or, and this is the truly wild part, maybe white holes disguise themselves so well that we're looking right at them without realizing it. Some theories even suggest that the Big Bang itself was a white hole event, the ultimate cosmic explosion birthing our universe. So while black holes are cosmic prisons with no escape, white holes could be cosmic launch pads, gateways to new realities or remnants of universes past. The math allows it. The physics teases the possibility. Now it's up to us to figure out whether these cosmic oddities are real or just a fascinating quirk of Einstein's equations. Either way, the idea alone reshapes how we think about the universe, and that's just the beginning of the mystery. Now, let's rewind the cosmic clock to uncover how white holes first entered the scientific conversation. The story begins in the 1960s, a golden age for theoretical physics, when Soviet scientist Igor Novikov took a bold step. He peered into Einstein's equations of general relativity, the same math that predicted black holes, and asked a revolutionary question. What if these equations held a mirror image of black holes, a celestial phenomenon where matter erupts instead of vanishes? Novikov's curiosity wasn't just wild speculation. He recognized that Einstein's field equations, which describe how matter and energy warp space-time, are symmetric. That means they don't care about the direction of time. Run them forward, and you get black holes. Run them backward, and voila, white holes emerge as a mathematical inevitability. Picture a film reel of a black hole's life played in reverse. Matter isn't sucked in, it's violently expelled. That's the elegant symmetry Novikov uncovered. But here's the twist. While black holes felt almost inevitable, massive stars collapsing under gravity was a plausible trigger, white holes lacked a clear origin story. Novikov proposed they might be relics of the universe's birth, or perhaps the other end of a black hole's journey. Imagine a black hole funneling matter into a singularity, only for that singularity to rebound as a white hole in another universe. It's a concept that stretches the imagination, but the math held up. Novikov wasn't working in isolation. Around the same time, other physicists like John Wheeler and Martin Kruskal were exploring similar ideas, dissecting Einstein's equations for hidden gems. Kruskal's work on space-time diagrams, for instance, revealed how black holes and white holes could be two sides of the same cosmic coin, connected through a theoretical bridge called an Einstein-Rosen bridge, what we now popularly call a wormhole. Yet, for all its mathematical beauty, the white hole theory faced skepticism. Why? Because unlike black holes, which had plausible formation mechanisms, white holes seemed to demand a cosmic magic trick, an explosion from nothing. Some physicists argued they were mere mathematical quirks, artifacts of equations with no real-world counterpart. Others, like Novikov, saw them as untapped potential, waiting for the right conditions or new physics to make them real. What's fascinating is how Novikov's ideas refused to fade. Decades later, his work resurfaces in cutting-edge theories like loop quantum gravity, where white holes reappear as quantum bounces, black holes reborn as white holes after billions of years. It's a testament to how one scientist's curiosity can ripple through time, challenging us to rethink the universe's rules. So while white holes remain elusive, their theoretical roots run deep. From Novikov's pioneering insight to today's quantum gravity debates, the quest to understand these cosmic anomalies continues. And who knows, the next breakthrough might just turn this mathematical marvel into observable reality. Now let's take a closer look at these cosmic twins, white holes and black holes side by side. At first glance, they might seem like polar opposites, but dig deeper, and you'll find a fascinating symmetry that ties them together. Think of a black hole as the universe's ultimate vacuum cleaner. Its gravitational pull is so intense that once matter crosses the event horizon, the point of no return, there's no escape, not even for light. Now flip that image. A white hole is like a cosmic fire hose, violently spewing out matter and energy. Nothing can enter a white hole's event horizon from the outside, just as nothing can leave a black hole's once it's inside. They're two sides of the same coin, bound by the same equations, but playing opposite roles in the cosmic drama. Here's where it gets even more intriguing. Both objects involve singularities, points where density becomes infinite, and the laws of physics, as we know them, break down. But while a black hole's singularity is hidden behind its event horizon, a white hole's singularity is naked, exposed for the universe to see. This challenges one of physics' sacred rules, Roger Penrose's cosmic censorship hypothesis, which suggests nature abhors naked singularities. If white holes exist, they could rewrite our understanding of space-time itself. The connection goes deeper when we consider wormholes. Some theories suggest that a black hole in one universe could be linked to a white hole in another, forming an Einstein-Rosen bridge. Picture a tunnel where matter falls into a black hole here and erupts from a white hole elsewhere, perhaps even in a different universe with entirely different physical laws. It's a speculative idea, but the math doesn't rule it out, leaving room for wild possibilities. But there's a catch. While black holes form from collapsing stars, white holes lack a clear birth mechanism. They'd need some explosive genesis, like a reversal of a black hole's collapse or a rebound from a quantum bounce. And unlike black holes, which we've detected through their effects on nearby stars and gas, white holes leave no obvious observational footprint unless, perhaps, they're hiding in plain sight as gamma-ray bursts or unexplained cosmic explosions. The bottom line: white holes and black holes share a profound mathematical kinship, but their realities diverge. One is a cosmic devourer, the other a cosmic fountain. One hides its secrets behind an event horizon, the other flaunts its singularity for all to see, yet both challenge us to rethink the very fabric of space and time. Whether they are truly twins or just distant relatives in the cosmic family tree, their story is far from over. Here's something that might completely reshape how you think about the origins of our universe. What if the Big Bang wasn't just an explosion of matter and energy, but actually a white hole in action? Let's unpack this mind-bending idea. Picture a white hole, an object that violently ejects everything inside it, never allowing anything to enter. Now imagine that event on a cosmic scale. The Big Bang fits that description eerily well. A singularity, a point of infinite density suddenly releasing all the matter, energy, and space-time we see today. It's as if our universe erupted from a white hole's event horizon, spewing out the building blocks of galaxies, stars, and eventually, us. This theory flips traditional cosmology on its head. Instead of the Big Bang being a one-off event with no clear predecessor, it could be the aftermath of something even grander. Some physicists suggest that our universe might be the other side of a black hole from another cosmos. In this scenario, matter collapsing into a black hole in a parent universe could rebound as a white hole in ours, creating what we perceive as the Big Bang. It's a cosmic recycling program on the ultimate scale. The implications are staggering. If true, white holes wouldn't just be hypothetical oddities, they'd be the very engines of creation. This challenges the long-held view that the Big Bang emerged from nothingness. Instead, it hints at a deeper continuity, where universes are born from the death throes of others. Suddenly, the idea of multiple universes isn't just science fiction. It's a plausible extension of the math behind Einstein's relativity. But here's the catch. The Big Bang as white hole idea struggles with one major question: where's the black hole that birthed it? In most models, white holes require an existing black hole to reverse or connect to. Yet we've never observed a black hole that could serve as our universe's progenitor. Some theorists argue that quantum gravity might resolve this, proposing that black holes could transform into white holes over unimaginable timescales. Others speculate that the parent universe's physics could be so different that its black holes behave in ways we can't yet imagine. Then there's entropy. The Big Bang began in a state of incredibly low entropy, something white holes struggle to explain. Normally, white holes would erupt in a high-entropy burst, more like a chaotic explosion than the finely tuned expansion we observe. This mismatch forces physicists to refine the theory, perhaps invoking quantum effects or new physics to bridge the gap. Yet for all its challenges, this idea holds a certain elegance. It links the largest and smallest scales of reality, tying the birth of our universe to the bizarre behavior of singularities. It suggests that creation isn't a singular miracle, but part of an endless cycle, where universes blossom from the remnants of others. Whether white holes truly explain the Big Bang remains an open question, but the possibility alone expands our cosmic imagination. What's next? Well, if white holes did play a role in the Big Bang, their echoes might still linger. Some researchers hunt for faint signatures in the cosmic microwave background, ancient light from the universe's infancy, that could betray a white hole's violent origins. Others model how quantum gravity might make such events possible. One thing's certain: the more we explore, the stranger and more wonderful our universe becomes. Now let's shift our gaze from the equations of physicists to the visions of storytellers. White holes might be elusive in reality, but they've found a vibrant life in science fiction, where they ignite our imagination with cosmic possibilities. Take Christopher Nolan's Interstellar, for example. While the film's black hole, Gargantua, stole the spotlight, its portrayal of higher dimensional space teased ideas eerily similar to white holes. The Tesseract scene, where Cooper navigates a folded spacetime, hints at a universe where gravity and time behave in ways that defy conventional physics, much like the theoretical chaos inside a white hole's eruption. Though never named outright, the film's climax dances with the spirit of white holes, a gateway of sorts, where the laws of cause and effect blur. Then there's Doctor Who, a series unafraid to play with cosmic extremes. In the episode, The Impossible Planet, the TARDIS team encounters a celestial object that defies logic, a potential nod to white holes' explosive nature. The show often uses such phenomena as plot devices, bending physics to serve its tales of time, travel, and alien civilizations. While these depictions prioritize drama over accuracy, they embed white holes in popular consciousness as symbols of the universe's untamed frontiers. But why do white holes captivate storytellers? Their inherent mystery plays a key role. A black hole's menace is visceral. It pulls, crushes, and consumes. A white hole, by contrast, is a cosmic rebel. It defies the pull of gravity, spitting out matter with violent creativity. This inversion makes it a perfect metaphor for rebirth or escape. In Event Horizon, though not explicitly a white hole, the ship's hellish dimension mirrors the idea of a universe birthed from chaos, a theme white holes embody perfectly. Yet sci-fi often takes liberties. Real white holes, if they exist, wouldn't be stable tunnels for spaceships or plot-convenient portals. They'd likely be brief, violent bursts, cosmic fireworks, fading almost instantly. The tension between scientific rigor and creative license is where the magic happens. Shows like Star Trek and books like The Three-Body Problem use white holes as springboards for existential questions. What lies beyond our universe? Could we ever harness such power? This cultural fascination reveals something deeper. White holes tap into our longing to explore the unknown. They're blank canvases for both scientists and artists, each projecting their hopes and hypotheses. Whether as narrative shortcuts or profound symbols, they remind us that the universe's weirdest corners inspire not just equations, but myths, dreams, and stories that endure. And speaking of stories, the next chapter of our cosmic journey takes us even deeper into the mathematics behind these enigmatic objects, where elegance and improbability collide. Now let's take a step beyond the realm of imagination and into the precise world of mathematics, where white holes reveal their true elegance. While pop culture plays with their explosive potential, physicists see something far more refined in these cosmic oddities. The beauty of white holes lies not in their spectacle, but in the equations that predict them, revealing a universe where symmetry and simplicity often hide in the most unexpected places. At the heart of this elegance is the Kruskal-Shekers diagram, a mathematical tool that maps the entire lifespan of a black hole, and by extension, its theoretical twin, the white hole. Imagine a graph where space and time curve and twist, creating pathways that defy our everyday intuition. In this diagram, a black hole's event horizon isn't just a point of no return, it's a gateway to a mirrored universe where time runs backward. The white hole emerges here as a sort of cosmic reflection, spewing out what the black hole devours. It's a solution so symmetrical it feels almost poetic, as if the universe itself enjoys a perfect balance. What makes this so compelling to physicists isn't just the math itself, but the way it mirrors deeper truths about reality. Einstein's field equations, which describe how matter and energy shape space-time, don't care which direction time flows. They're time-symmetric, meaning the equations work just as well whether you're watching a cup shatter or miraculously reassemble. White holes fit neatly into this picture as the time-reversed versions of black holes, a mathematical inevitability that hints at a universe far stranger than we often assume. But why do scientists cling to such an improbable idea? Part of it is the sheer elegance of the solution. In physics, beauty often guides discovery. When an equation balances perfectly, when a theory explains multiple phenomena with minimal assumptions, it's a sign that we're onto something profound. White holes, though likely unstable or short-lived in reality, emerge naturally from the math without needing any extra rules or forces. They're not tacked on, they're woven into the fabric of general relativity itself. Take the concept of geodesics, the paths that objects naturally follow in curved spacetime. Near a black hole, these paths spiral inward, trapped by gravity's grip. Near a white hole, they'd spiral outward, as if repelled by some invisible force. The math treats both scenarios with equal validity, painting a universe where creation and destruction are two sides of the same coin. This duality fascinates theorists, offering a glimpse into how the cosmos might balance its books on the grandest scales. Of course, elegance alone doesn't make something real. The same equations that predict white holes also suggest they'd collapse instantly, crushed by their own outbursts, yet their mathematical inevitability keeps them alive in the minds of physicists. They're a reminder that the universe's rules often outpace our imagination, offering puzzles that are as beautiful as they are baffling. And as we ponder these equations, we're left with a tantalizing question. If the math insists white holes are possible, could nature find a way to stabilize them? The answer might lie in the quantum realm, where the rules of gravity and particles collide, a frontier we'll explore next. Now, as we shift our gaze from the elegance of equations to the cutting edge of cosmic debate, the question becomes unavoidable: could white holes actually exist? This isn't just theoretical speculation, it's a heated discussion dividing physicists, with compelling cases on both sides. On one hand, critics argue that white holes violate everything we know about cosmic stability. Picture a star collapsing into a black hole. Now imagine that process reversed, matter erupting outward with enough force to birth a new universe. The problem: energy doesn't just appear out of nowhere. Our universe runs on rules like conservation of mass and energy, and white holes seem to flout them spectacularly. Worse, general relativity suggests they'd self-destruct instantly, crushed by the very outpouring that defines them. It's like trying to keep a shaken soda bottle from exploding. Nature abhors that kind of imbalance. But here's where the debate gets fascinating. Defenders of white holes, like physicist Carlo Rovelli, propose a quantum loophole. In his quantum bounce theory, a dying black hole might not vanish but rebound as a white hole, like a cosmic phoenix. This isn't science fiction, it's a consequence of quantum gravity, where spacetime itself becomes granular at the tiniest scales. Imagine a black hole shrinking to the size of an atom, then hitting a limit where it can't compress further. The pent-up energy might then bounce outward, creating a white hole's explosive rebirth. It's a stretch, but so were black holes once. Skeptics counter that even quantum corrections wouldn't stabilize white holes long enough to matter. Yet Rovelli's calculations suggest otherwise. His models show that while classical white holes would vanish in microseconds, quantum effects could stretch their lifespan to billions of years, enough to leave traces in our universe. Think of it like a frozen firework, normally fleeting, but under quantum rules, it might linger just long enough to spot. Then there's the observational angle. If white holes exist, where are they? Some theorists propose that gamma-ray bursts, those violent flashes in deep space, could be their death throes. Others argue that primordial white holes, born in the Big Bang's chaos, might now lurk as dark matter. It's speculative, but so was dark matter itself until we saw its gravitational fingerprints. Ultimately, the debate boils down to a clash of philosophies. Are white holes just mathematical ghosts, or is nature sneakier than we think? Every time we've bet against Einstein's equations, like with gravitational waves, we've lost. Maybe white holes are next, or maybe they're a beautiful dead end, but as we'll soon see, their potential ties to wormholes and multiverses keep pulling us back into the mystery. Now, let's take this cosmic puzzle one step further and ask a mind-bending question. Could white holes be the secret passageways to other universes? This is where the lines between black holes, white holes, and wormholes start to blur in the most fascinating way. Picture a wormhole, the ultimate shortcut through spacetime, often depicted in sci-fi as a glowing tunnel connecting distant points in the universe. In theory, a wormhole requires two mouths, one where matter enters and another where it exits. Here's the twist. Some physicists speculate that the entrance could be a black hole, while the exit might be a white hole. Think of it like a cosmic subway system, where a black hole sucks you in, and a white hole spits you out somewhere entirely new, maybe even in another universe. But before we get too carried away, let's ground this in real physics. Einstein's equations actually allow for wormholes, known as Einstein-Rosen bridges. These aren't science fiction, they're mathematical possibilities. The catch: traditional wormholes would collapse instantly under their own gravity, making them useless for travel. That's where white holes come in. If a white hole could stabilize the other end, acting as a cosmic exhaust vent, it might just keep the wormhole open long enough to be traversable. Now, here's the problem. Even if this exotic tunnel existed, passing through it would be complicated. The forces near a black hole's event horizon would stretch you into spaghetti, while the white hole's explosive output might shred you apart. Not exactly a five-star travel experience, but quantum physics offers a glimmer of hope. If the wormhole's throat could be lined with exotic matter, a hypothetical substance with negative energy, it might counteract the crushing forces, making the journey survivable. The implications are staggering. If white holes and wormholes are linked, they could explain more than just interstellar travel. They might be the birthplaces of new universes. Imagine a black hole in our universe collapsing into a white hole in another, sparking a big bang on the other side. This idea, called black hole cosmology, suggests that every black hole in our cosmos could be seeding a new universe inside it, with white holes as the exit points. Skeptics, of course, raise valid concerns. No one's ever seen a wormhole, let alone a white hole anchoring one, and exotic matter. It's purely theoretical. But remember, black holes were once just equations on paper too. The real takeaway is this: if white holes exist, they might not just be cosmic oddities. They could be the missing piece in a grander puzzle, tying together black holes, wormholes, and even the multiverse. Up next, we'll explore how Stephen Hawking's most famous discovery might change everything we think about white holes and their place in the cosmos. Now, let's turn our attention to a groundbreaking idea that could reshape how we think about white holes. Enter Stephen Hawking and his revolutionary discovery of black hole radiation. This concept, known as Hawking radiation, might hold the key to understanding whether white holes could exist, or even how they might behave. Hawking's work showed that black holes aren't entirely black. Due to quantum effects near the event horizon, they slowly emit particles, losing energy over time. This means black holes have a life and they evaporate, fading away in a final burst of radiation. But here's where things get interesting. If black holes can radiate energy, what does that imply for their theoretical opposites, white holes? Some physicists suggest that white holes might exhibit a kind of reverse Hawking radiation. Instead of emitting particles as they shrink, they could absorb them as they grow. Imagine a white hole as a cosmic fountain, constantly spraying out matter and energy, but if it's also pulling in radiation from its surroundings, that could create a delicate balance, making it more stable than we once thought. The implications are wild. If white holes emit and absorb energy in a predictable way, they might leave behind detectable signatures. For instance, astronomers could hunt for unexplained bursts of high-energy particles in space that don't fit known phenomena like supernova or gamma-ray bursts. These anomalous events might just be white holes announcing their presence, but there's a catch. Hawking radiation is incredibly faint for large black holes, taking trillions of years to make a noticeable difference. If white holes follow a similar rule, their radiation might be equally hard to spot, and if they're as rare as some theories suggest, finding one would be like searching for a single grain of sand in a desert. Still, the possibility is tantalizing. If white holes do interact with Hawking radiation, it could solve one of their biggest theoretical problems: instability. Traditional models suggest white holes would explode the moment they form, but quantum effects might smooth out their violent outbursts, allowing them to persist longer. This could mean white holes aren't just fleeting cosmic fireworks, but lasting structures in the universe. So, what's the verdict? Hawking's work opens a door to reimagining white holes not as mathematical curiosities, but as real, detectable objects. They might be hiding in plain sight, disguised as unexplained cosmic events, and if we ever find one, it could revolutionize our understanding of black holes, time, and even the birth of universes. Up next, we'll explore an even bolder idea: what if white holes aren't just cosmic oddities, but the missing pieces of the dark matter puzzle? Now, let's venture into one of the most intriguing possibilities in modern cosmology. What if white holes aren't just theoretical oddities, but the hidden architects of the universe's greatest mystery, dark matter? For decades, scientists have grappled with the enigma of dark matter, the invisible substance that makes up roughly 27% of the universe's mass. We know it's there because of its gravitational effects on galaxies, but no one has directly detected it. Could white holes, or their remnants, be the missing piece? Some bold theories suggest they might. Imagine this: as black holes evaporate through Hawking radiation, they might not vanish entirely. Instead, they could leave behind ultra-dense remnants, objects so tiny yet so massive they're nearly undetectable. These remnants, some physicists argue, could behave like white holes in their final stages, constantly emitting and reabsorbing energy in a quantum dance. If these remnants exist in vast numbers, scattered across the cosmos, their collective gravity could mimic the effects of dark matter. The idea isn't as far-fetched as it sounds. Research papers have explored how quantum corrections to general relativity could allow for stable remnants of black holes, often called Planck stars or quantum black holes. These objects, theorized to be about a trillionth the size of an atom, but with the mass of a mountain, would interact weakly with light and ordinary matter, just like dark matter. They'd be invisible to telescopes, but exert a gravitational pull on their surroundings. But not everyone is convinced. Critics point out several hurdles. For one, if white hole remnants were dark matter, we'd expect to see their emissions tiny bursts of energy as they absorb and release particles. So far, no such signals have been conclusively detected. Second, the sheer number of remnants needed to account for dark matter's observed effects would require an unimaginable density of primordial black holes, something current models struggle to explain. Then there's the question of formation. If these remnants come from dying black holes, how did enough black holes form in the early universe to leave behind sufficient remnants? Some theories propose exotic processes, like quantum fluctuations during the Big Bang, but these remain speculative. Despite the challenges, the idea refuses to fade. It's a testament to how white holes, even as hypothetical objects, continue to push the boundaries of physics. If future observations uncover unexplained gravitational anomalies or mysterious energy bursts, we might just find that white holes, or their ghostly remnants, have been hiding in plain sight all along. Up next, we'll tackle another mind-bending twist. What if white holes aren't just objects in space, but reflections of time itself? Now, let's twist our perspective even further. What if white holes aren't just cosmic opposites of black holes, but black holes themselves, rewound like a film played in reverse? This is the time reversal paradox, a concept that turns our understanding of cause and effect on its head. At first glance, the math seems to support this wild idea. Einstein's equations don't care about the direction of time. They're symmetric, meaning a black hole's collapse and a white hole's explosion could be two sides of the same event, separated only by time's arrow. Picture a black hole swallowing matter relentlessly. Now, imagine hitting rewind. That infalling matter would burst outward, precisely what a white hole does. To an outside observer, a white hole might just look like a black hole running backward in time. This raises profound questions about causality. In our everyday world, causes always come before effects. But if white holes are time-flipped black holes, does that mean events inside them unfold in reverse? Could a white hole's eruption cause the black hole's formation in its past? Physicists call this retrocausality, and it's as unsettling as it sounds. It challenges the very foundation of how we perceive time, suggesting that the future might influence the past in ways we can't yet comprehend. The paradox deepens when we consider quantum mechanics. At tiny scales, particles don't always follow strict cause and effect rules. Quantum events can appear probabilistic, even spooky, as Einstein once said. Some theories, like quantum loop gravity, propose that white holes could emerge from black holes when quantum effects dominate, effectively resetting the timeline at the singularity. If true, this would mean black holes don't just end in oblivion, they might rebirth as white holes, with time itself folding back. But here's the catch. If white holes are black holes in reverse, why don't we see them everywhere? Black holes are common, yet white holes remain elusive. One explanation is entropy, the universe's tendency toward disorder. Running time backward would decrease entropy, violating the second law of thermodynamics. Nature seems to favor the forward march of time, making white holes incredibly rare, if they exist at all. Another hurdle is observation. If a white hole is a black hole playing backward, detecting one would require witnessing its entire timeline, something impossible given their hypothetical lifetimes. Even if they exist, their signals might be indistinguishable from cosmic noise, like gamma-ray bursts or quantum fluctuations. Despite these challenges, the time reversal idea captivates physicists because it unifies two cosmic extremes under one elegant framework. It suggests that black holes and white holes aren't separate entities but different phases of the same object, linked by the flow of time. This could revolutionize our understanding of singularities, gravity, and even the birth of universes. Up next, we'll explore how quantum gravity might breathe new life into white holes, transforming them from mathematical curiosities into testable predictions. Now, let's step into the cutting edge of physics, where the rules of the very small meet the mysteries of the cosmos. Quantum gravity, the long-sought theory meant to unite Einstein's relativity with quantum mechanics, might hold the key to unlocking white holes in a way that defies classical intuition. Imagine a black hole's fate under the lens of quantum gravity. In the classical world, a black hole's singularity is a one-way street to infinite density. But quantum mechanics abhors infinities. It smooths out sharp edges, suggesting that at some point, the collapse must stop. This is where loop quantum gravity enters the picture. It proposes that spacetime itself is made of tiny, indivisible loops. Think of it as a cosmic fabric woven from threads. When a black hole reaches its smallest possible size, these loops could bounce, turning the collapse into an explosion. The result, a quantum white hole born from the ashes of a black hole's demise. String theory offers another fascinating twist. In this framework, particles aren't dots but vibrating strings. Some versions suggest that black holes could transform into fuzzballs, tangled knots of strings with no singularity. If a fuzzball unravels, it might release its energy in a burst akin to a white hole's eruption. These theories aren't just mathematical fantasies. They make testable predictions, like specific energy signatures or echoes in gravitational waves that telescopes like LIGO or future missions could detect. What's revolutionary here is the timeline. A quantum white hole wouldn't take billions of years to form. Calculations suggest it could pop into existence almost instantly on cosmic scales. This solves the entropy problem, too. Quantum effects could allow a white hole to erupt without violating thermodynamics, neatly sidestepping the time reversal paradox we discussed earlier. But how would we spot one? Quantum white holes might leave fingerprints in high-energy cosmic rays or fleeting bursts of radiation. Some physicists even speculate that certain fast radio bursts, those mysterious, powerful signals from deep space, could be white holes announcing their presence. The challenge is distinguishing these from other cosmic phenomena, but new instruments are making it possible to hunt for these subtle clues. The implications are staggering. If quantum gravity resurrects white holes, it would mean black holes aren't eternal prisons but cosmic recyclers, turning destruction into creation. This could reshape our understanding of the universe's life cycle, suggesting that every collapse might seed a new beginning. As we push the boundaries of physics, white holes stand at the crossroads of theory and observation. Next, we'll venture into the multiverse, where white holes might not just be rebirths, they could be gateways to entirely new universes with laws unlike our own. Now, let's stretch our imagination even further and explore how white holes might not just be cosmic curiosities, they could be the very bridges to other universes. Picture this: every time a white hole erupts, it doesn't just spew matter and energy into our universe. Instead, it might birth an entirely new cosmos, complete with its own laws of physics. This idea ties white holes to one of the most mind-bending concepts in modern science, the multiverse. Think of a white hole as a cosmic pressure valve. When a black hole collapses in our universe, its singularity might not vanish into nothingness. Under quantum gravity's rules, that singularity could rebound as a white hole in another spacetime, new universe with its own dimensions, forces, and constants. Some theories suggest these baby universes could have wildly different properties. Gravity might be stronger, light slower, or even the number of dimensions might vary. It's as if every black hole in our universe is a seed for another reality, with white holes as the delivery mechanism. This isn't just speculative fiction. Physicists like Lee Smolin have proposed the idea of cosmological natural selection, where universes reproduce through black holes birthing new ones via white holes. In this scenario, universes with more black holes would spawn more offspring, leading to a cosmic Darwinism where successful physics, like ours, becomes common across the multiverse. It's a daring twist on evolution, applying it to the fabric of reality itself. String theory adds another layer. If higher dimensions exist, white holes might not just connect to parallel universes, but to brains, floating membranes of reality in a higher dimensional space. A black hole in our brain could tunnel through this space and emerge as a white hole in another, funneling matter and energy into a universe we'll never see. This could explain why our universe's constants seem finely tuned for life. If countless universes exist, statistically, some would inevitably have the right conditions, and we'd find ourselves in one. But how would we test such a radical idea? Indirect clues might come from anomalies in cosmic microwave background radiation or unexplained gravitational waves. If a white hole in another universe leaked energy into ours, it could leave faint imprints. Some researchers even suggest that dark energy, the mysterious force accelerating our universe's expansion, might be the subtle push from adjacent universes connected via white holes. The implications are profound. If white holes are multiverse gateways, our universe might be one of countless bubbles in a froth of realities, each with its own story. It challenges the very notion of the universe, suggesting we're part of something far grander, a cosmic network where creation and destruction are endlessly linked. As we ponder these possibilities, one question lingers: could we ever traverse these gateways that leads us to the next frontier, white holes and wormholes, and whether they could stitch the multiverse into a navigable tapestry? Now, let's tackle one of the biggest puzzles in this cosmic mystery. How do we even begin to detect something as elusive as a white hole? After all, if they exist, they're not exactly sending out invitations. The very nature of white holes makes them fiendishly difficult to observe. Unlike black holes, which announce their presence by pulling matter in, white holes would theoretically push everything away, making them cosmic loners. So, how do we spot something that doesn't want to be seen? First, consider their fleeting existence. Many theories suggest white holes would be incredibly short-lived. Imagine a cosmic firework, a brilliant burst of energy and matter that vanishes almost as quickly as it appears. If a white hole erupted in deep space, we might only have a split second to catch it before it fades into oblivion. This means our telescopes and detectors would need to be in the right place at the right time. A bit like trying to photograph a shooting star with your eyes closed. But here's where it gets interesting. Even if we can't see white holes directly, they might leave behind clues. One tantalizing possibility is gamma-ray bursts, some of the most energetic explosions in the universe. While most gamma-ray bursts are tied to collapsing stars or merging neutron stars, a handful defy explanation. Could these outliers be the fingerprints of white holes? Some physicists speculate that a white hole's violent outburst could mimic the signature of a gamma-ray burst, offering a potential way to identify them indirectly. Another clue might come from unexplained cosmic explosions. Take fast radio bursts, for example, brief, intense pulses of radio waves from distant galaxies. While many origins have been proposed, from magnetars to alien civilizations, a white hole's sudden release of energy could theoretically produce a similar signal. The key would be finding a burst that doesn't fit any known astrophysical profile, a cosmic anomaly that points to something entirely new. Then there's the gravitational wave angle. Since white holes would warp spacetime just like black holes, their formation or death might send ripples through the fabric of the universe. Gravitational wave observatories like LIGO and Virgo could, in theory, pick up these disturbances. The challenge: distinguishing a white hole's signal from the countless other cosmic events that create gravitational waves. It's like trying to hear a whisper in a crowded room. But perhaps the most intriguing possibility lies in the cosmic microwave background, the faint glow left over from the Big Bang. If a white hole erupted in the early universe, it could have left subtle imprints in this radiation, like a shadow on a photograph. Researchers have even proposed scanning the cosmic microwave background for odd patterns or asymmetries that might hint at white hole activity. Of course, all of this is easier said than done. The universe is vast, and white holes, if they exist, are needles in a cosmic haystack. Yet, the hunt for these elusive objects pushes our technology and imagination to the limit. Every unexplained signal, every anomalous burst, could be a breadcrumb leading us closer to uncovering one of the universe's best-kept secrets. So, while white holes remain hidden for now, the search itself is reshaping how we think about the cosmos. It's a reminder that sometimes the most profound discoveries come from chasing the unobservable until it finally reveals itself. And who knows, the next big breakthrough might be just one telescope scan away. This brings us to another fascinating twist. What if white holes aren't just cosmic oddities, but the key to solving one of physics' greatest mysteries? That's a story for another section, but for now, keep your eyes on the skies. The universe still has plenty of surprises up its sleeve. Now, let's take a step into one of the strangest corners of cosmology, where white holes collide with a mind-bending thought experiment, the Boltzmann brain paradox. Imagine this: if white holes can erupt unpredictably, spewing out energy and matter, could one of these random cosmic events accidentally create a self-aware consciousness? Sounds like science fiction, but it's a serious question that physicists have wrestled with for decades. The Boltzmann brain paradox comes from a quirky idea in thermodynamics. In an infinitely old universe, random fluctuations in entropy could, theoretically, assemble a fully formed, conscious brain out of pure chaos. It's like shaking a box of Scrabble tiles forever, and suddenly they spell out the complete works of Shakespeare. The odds are astronomically low, but given enough time, even the most improbable events become possible. Now, apply that to white holes. If a white hole's eruption is a burst of energy and matter, could it, by sheer chance, arrange particles in just the right way to form a thinking mind? This isn't just wild speculation. Some theories suggest that white holes, especially in the early universe, might have been more common. If that's the case, the sheer number of eruptions increases the chances of something bizarre happening. Think of it like rolling a cosmic dice trillions of times. Eventually, you might get a roll that defies all expectations. The unsettling implication: if consciousness can emerge randomly from a white hole's outburst, how do we know we're not the product of such a fluke? But here's where things get even weirder. If a Boltzmann brain did spontaneously appear, it would likely exist for only a split second before dissolving back into chaos. Its entire life would be a fleeting moment of awareness, perhaps filled with false memories of a past that never happened. This raises a chilling question. How could we ever prove our memories and experiences are real, and not just the brief hallucination of a particle arrangement gone right? Physicists have proposed ways to dodge this paradox. One argument is that universes that produce too many Boltzmann brains would be statistically overwhelming, making it far more likely that we're in a universe where stable, ordered consciousness like ours is the norm. Another idea ties back to quantum mechanics. Perhaps the rules of reality prevent such random consciousness from forming in the first place, but white holes throw a wrench into these solutions. If they're as chaotic as theory suggests, they could be the ultimate wild cards, making Boltzmann brains more plausible than we'd like to admit. So, where does this leave us? The Boltzmann brain problem forces us to confront the fragility of our own existence. It's a humbling reminder that the universe might not care about order, meaning, or even consciousness. Yet, it also highlights how white holes aren't just cosmic curiosities. They could be the key to understanding the deepest mysteries of reality. Whether they're birthing minds or simply scattering energy, they challenge us to rethink what's possible in the vast, unpredictable expanse of space and time. And with that, we're left staring into the cosmic abyss, wondering if the universe is playing a game we're only beginning to understand. But don't let that unsettle you. After all, if we are Boltzmann brains, we probably won't exist long enough to worry about it. Now, let's turn to another fascinating twist in the white hole saga, one that ties them to the very fabric of time itself. Stay tuned, because the next section will bend your mind in ways you never saw coming. Now, let's pivot to something equally mesmerizing: how white holes weave themselves into the fabric of alternative cosmologies. These aren't your everyday theories about the universe. They're bold, boundary-pushing ideas that challenge everything we think we know. And white holes, they might just be the missing puzzle piece in some of these radical models. Take Roger Penrose's conformal cyclic cosmology, for example. This theory suggests that the universe doesn't just have one Big Bang, it has countless ones, over and over, in an endless cycle. Here's how it works. As our universe expands and fades into a cold, empty void, all that's left is radiation. But at a certain point, this radiation becomes so uniform that the universe effectively resets, triggering a new Big Bang. Now, where do white holes come in? Penrose proposes that the singularities inside black holes, those infinitely dense points, could transform into white holes in the next cycle, spewing out matter and energy to birth a fresh universe. It's as if black holes are cosmic seeds, and white holes are the blossoms of new realities. Then there's the bouncing universe theory, which flips the idea of a one-time Big Bang on its head. Instead of a singular beginning, this model suggests our universe is part of an eternal bounce, expanding, contracting, and then expanding again. In this scenario, white holes could be the remnants of a previous universe's collapse, funneling energy and matter back into existence as the next cycle begins. Think of it like a cosmic heartbeat, with white holes acting as the pulse that jumpstarts a new phase. But why should we care about these alternative models? Because they offer a way to sidestep some of the biggest headaches in cosmology, like the mystery of what happened before the Big Bang. If white holes are gateways between cycles, they could explain how information and structure carry over from one universe to the next. It's a tantalizing thought that the laws of physics might not be arbitrary, but inherited from an earlier incarnation of reality. Of course, not everyone's convinced. Critics argue that these theories are speculative, lacking the hard evidence needed to move from fascinating ideas to accepted science. Yet, that's the beauty of white holes. They force us to ask questions we wouldn't otherwise consider. Whether they're part of Penrose's cycles or the engine of a bouncing cosmos, they remind us that the universe is far stranger and far more creative than we've dared to imagine. So, what's the takeaway? White holes don't just belong to the realm of traditional physics. They're wild cards in the grand game of cosmology, popping up in theories that redefine time, space, and existence itself. And as we push the boundaries of what's possible, one thing becomes clear: the universe still has plenty of secrets left to reveal. Next up, we'll tackle an equally perplexing question: how do white holes play with one of the most unbreakable laws of physics, the second law of thermodynamics? Trust me, it's going to get even more intriguing. Now, let's untangle one of the most puzzling questions about white holes: how they square with the unshakable laws of thermodynamics. The second law, in particular, is a cosmic rule that seems almost sacred. Entropy, or disorder, always increases over time. It's why your coffee cools down, why ice melts, and why the universe marches inexorably toward chaos. But white holes, by their very nature, appear to flip this script. They spew out matter and energy in a perfectly ordered way, like a cosmic fountain defying gravity. So, do they break physics' most ironclad law? Here's where things get fascinating. On the surface, white holes seem to violate the second law by decreasing entropy locally. Imagine a white hole ejecting a stream of pristine particles, no randomness, no decay, just pure, organized energy. But physicists like Leonard Susskind argue there's a loophole. The key lies in the bigger picture. While the white hole's output might appear orderly, its very existence could be tied to a black hole's past, a black hole that gobbled up matter and maximized entropy long before. In this view, the white hole isn't cheating thermodynamics. It's playing catch-up, balancing the books by releasing what its black hole counterpart once consumed. Think of it like a cosmic ledger. A black hole swallows a star, increasing entropy as the star's structure dissolves into chaos. Later, a white hole settles the debt by ejecting that energy back out. The total entropy of the universe still increases overall. It's just distributed across time and space in a way that lets white holes seem like rebels. Susskind's black hole complementarity theory takes this further, suggesting that from an outside observer's perspective, the two might even be indistinguishable, like two sides of the same coin. But not all physicists agree. Some argue that white holes, if they exist, would need a mechanism to preserve entropy's relentless rise. One provocative idea ties them to quantum gravity. In theories like loop quantum gravity, white holes could emerge as quantum bounces, black holes that reach a maximum density and rebound, but with quantum effects ensuring entropy still climbs. It's as if the universe has a failsafe to keep thermodynamics intact, even in the face of cosmic oddities. So, where does this leave us? White holes don't so much break the rules as bend them in ways we're still deciphering. They force us to ask, is entropy truly local, or is it a cosmic sum game? And could the second law be more flexible than we thought? Whether through Suskind's ledger or quantum bounces, white holes remind us that even physics' strictest laws might have hidden depths, and that's what makes them so thrilling to explore. Up next, we'll dive into another enigma. Could white holes hold the key to solving one of physics' biggest headaches, the black hole information paradox? Strap in, it's about to get even wilder. Here's where the plot thickens. The black hole information paradox has haunted physicists for decades, and white holes might just hold the key to solving it. Imagine throwing a book into a black hole. According to Einstein's theory, that book and all the information it contains should be lost forever, crushed into a singularity. But quantum mechanics insists information can never truly vanish. So, who's right? Enter white holes, the cosmic wildcards that could reconcile these two conflicting ideas. The paradox boils down to this: black holes evaporate over time, thanks to Hawking radiation. But if they vanish, what happens to all the information they swallowed? Stephen Hawking initially thought it was destroyed, which would shatter quantum mechanics' core principle that information is always preserved. This sparked a decades-long debate, with luminaries like Leonard Susskind and Gerard T. Hooft arguing that information must escape somehow. That's where white holes come in. Picture a black hole as a cosmic shredder, and a white hole as its mysterious twin that tapes the pieces back together. Some theories suggest that information swallowed by a black hole isn't lost. It's just stored temporarily, like data, in a scrambled hard drive. When the black hole's lifespan ends, it might transform into a white hole, spewing that information back out in a burst of radiation or particles. It's as if the universe has a failsafe to prevent data loss, with white holes acting as the ultimate recycling system. Carlo Rovelli, a pioneer in loop quantum gravity, takes this even further. His quantum bounce theory proposes that black holes don't just fade away, they rebound as white holes at the quantum level, releasing trapped information in the process. This wouldn't happen instantly. It could take billions of years, far longer than the current age of the universe. But mathematically, it offers a neat solution. Information isn't destroyed, just delayed. Not everyone's convinced, though. Critics point out that this idea hinges on speculative physics, like quantum gravity effects we've yet to observe. Plus, if white holes do spit out information, how would it even look? Would it be garbled beyond recognition or perfectly preserved? Some models suggest the data might emerge encoded in Hawking radiation, like a cosmic Morse code. Others propose it could be jumbled, requiring a hypothetical decoder to make sense of it. The stakes are high. If white holes can resolve the information paradox, they'd bridge the gap between general relativity and quantum mechanics, a holy grail of physics. But until we detect one or crack the quantum gravity code, it remains a tantalizing what if. What's clear is that white holes force us to rethink not just black holes, but the very nature of reality. Are they the universe's way of keeping its books balanced? The answer might rewrite physics as we know it. Coming up, we'll tackle an even bolder idea: whether white holes defy one of cosmology's most famous conjectures, the cosmic censorship hypothesis. Could these cosmic rebels expose naked singularities to the universe? Stay tuned. Let's shift gears and dive into one of the most provocative debates in theoretical physics: cosmic censorship. Imagine a universe where the very fabric of reality could tear open, exposing raw singularities to the cosmos. That's the nightmare scenario physicist Roger Penrose sought to prevent with his cosmic censorship hypothesis, a bold conjecture that essentially says, no naked singularities allowed. But here's the twist: white holes might be the ultimate rule breakers, threatening to unravel this cosmic order. Penrose's idea is simple but profound. Singularities, those infinitely dense points at the heart of black holes, are always hidden behind event horizons, the boundaries beyond which nothing escapes. This cosmic cover-up ensures that the bizarre, physics-breaking effects of singularities don't wreak havoc on the observable universe. Without an event horizon, a naked singularity would defy the laws of physics as we know them, making the future unpredictable. It's like having a cosmic spoiler for reality, where cause and effect no longer apply. But white holes throw a wrench into this tidy picture. By definition, a white hole is a singularity with no event horizon blocking its interior from view. Matter and energy erupt outward uncontrollably, exposing the singularity to the universe. If white holes exist, they'd be the ultimate naked singularities, flaunting their defiance of Penrose's censorship. This isn't just a theoretical curiosity, it challenges the very foundations of predictability in physics. Could the universe tolerate such rebels, or would their existence force us to rewrite the rules? Supporters of cosmic censorship argue that nature abhors a naked singularity, and that some mechanism, perhaps quantum gravity, must always shroud them. After all, we've never observed one, but critics counter that white holes, if real, would be the exception. Carlo Rovelli's quantum bounce theory, for instance, suggests that a black hole's transformation into a white hole might briefly reveal a singularity before it dissipates. Even that fleeting exposure could have profound implications, like unpredictable bursts of energy or space-time ripples that defy classical physics. The stakes couldn't be higher. If naked singularities exist, even momentarily, they'd create regions where Einstein's equations fail, and the deterministic universe we know gives way to chaos. Imagine a place where gravity fluctuates wildly, time loops unpredictably, and the very notion of before and after loses meaning. It's a physicist's puzzle and a philosopher's playground, raising questions about whether the universe truly guards its secrets, or if white holes are the key to unlocking them. So where does this leave us? The cosmic censorship hypothesis remains unproven, and white holes are its greatest challengers. Whether they're cosmic glitches or features of a deeper reality, one thing is clear: the debate forces us to confront the limits of our theories. Next, we'll explore an even stranger possibility: that white holes might not be exotic anomalies, but fleeting quantum fluctuations at the smallest scales of existence. Are they hiding in plain sight, woven into the fabric of space-time itself? Let's find out. Now, let's take a step even deeper into the quantum realm, where the rules of gravity and particle physics blur into something far stranger. Picture the fabric of space-time not as a smooth, unbroken surface, but as a bubbling sea of energy, constantly churning at the smallest scales imaginable. This is the world of quantum foam, a turbulent, ever-changing landscape where tiny particles wink in and out of existence in fractions of a second. And here's the wild idea. What if white holes aren't just cosmic oddities lurking in distant space, but fleeting bursts of energy right under our noses, hidden in this quantum chaos? At the Planck scale, the smallest possible size in the universe, space-time itself becomes grainy, like the static on an old TV. In this bizarre domain, the vacuum of space isn't empty at all. It's a frothing soup of virtual particles that appear and vanish, borrowing energy from nothingness before returning it almost instantly. But sometimes, under extreme conditions, these quantum fluctuations might not fully cancel out. That's where white holes could enter the picture, not as stable, galaxy-sized objects, but as momentary flashes in the quantum foam. Imagine a tiny singularity erupting outward, spewing energy for a split second before dissolving back into the void. This idea ties white holes directly to vacuum energy, the mysterious force behind the universe's expansion. If spacetime is constantly bubbling with energy, could some of those bubbles briefly behave like microscopic white holes? Theoretical physicist John Wheeler once speculated that at these scales, spacetime might be so warped that it creates temporary tunnels or spacetime worms. While his original concept focused on wormholes, the same logic could apply to white holes, transient bursts that defy classical physics before vanishing without a trace. The implications are mind-bending. If white holes flicker in and out of existence at the quantum level, they could leave behind subtle signatures, perhaps odd bursts of radiation or tiny gravitational ripples. These wouldn't resemble the dramatic explosions of their theoretical larger cousins, but they'd still challenge our understanding of energy conservation and causality. After all, if a microscopic white hole erupts unpredictably, even for an instant, it could momentarily scramble the laws of physics in its immediate vicinity. Some researchers, like those working on loop quantum gravity, suggest these quantum white holes might not just be random noise. They could be the remnants of black holes that have undergone a quantum bounce, emerging as fleeting white holes before fully evaporating. This would mean that every black hole's death might spark a brief white hole phase, like the last flash of a dying ember. If true, the universe could be teeming with these tiny, invisible fireworks, each one a whisper of a singularity's final act. Of course, detecting such phenomena is a monumental challenge. Planck-scale physics operates far beyond the reach of current technology, and these hypothetical white holes would be unimaginably small and short-lived. But their potential existence forces us to rethink the boundaries between quantum mechanics and general relativity. Are white holes hidden in the quantum foam, woven into the very fabric of spacetime? The answer might lie at the intersection of black hole thermodynamics, vacuum energy, and the untamed frontier of quantum gravity. So while we may never observe a quantum white hole directly, their theoretical possibility reminds us that the universe is far stranger than it appears. From the vastness of cosmic singularities to the froth of the quantum void, white holes continue to defy easy explanation, keeping physicists guessing and our imaginations alight. Next, we'll turn our gaze to an even bigger question. Could these enigmatic objects hold the key to the Fermi paradox, the eerie silence of the cosmos? Stay tuned. Now, let's venture into one of the most tantalizing mysteries of the cosmos, the Fermi paradox, the puzzling silence of the universe despite its vastness. If life is statistically likely to arise elsewhere, why haven't we detected any signs of advanced civilizations? Here's where white holes, those enigmatic cosmic twins of black holes, might offer a radical explanation. Could it be that advanced civilizations have already harnessed white holes as power sources or interstellar highways, leaving no trace for us to find? Imagine a civilization so advanced that it has unlocked the secrets of white holes. Unlike black holes, which devour everything in their path, white holes eject matter and energy outward. If controlled, this explosive output could serve as an unimaginably powerful energy source, far surpassing anything we know. Picture a society tapping into these cosmic geysers, drawing energy from the very fabric of space-time to fuel their cities, starships, or even their experiments in creating new universes. If such civilizations exist, their reliance on white holes might render traditional energy signatures like radio waves or Dyson spheres obsolete, making them invisible to our telescopes. But the possibilities get even wilder. What if white holes aren't just power plants but gateways? Some theories suggest that black holes and white holes could be connected via wormholes, forming shortcuts through spacetime. If advanced beings have mastered this technology, they might be zipping across the cosmos through these tunnels, bypassing the need for slow, conventional travel. This could explain why we haven't encountered them. They're not traveling through the universe as we imagine, but slipping through hidden corridors in the fabric of reality itself. Then there's the darker side of this speculation. If white holes are as volatile as they seem, wielding them could come with catastrophic risks. A misfire might rip apart entire star systems or unravel spacetime in unpredictable ways. Perhaps civilizations that attempted to harness white holes have inadvertently erased themselves from existence, leaving behind only cosmic silence. It's a grim thought, but one that fits the eerie absence of contact we've observed. Of course, this is all speculative, and critics argue that white holes remain purely theoretical, far from being practical tools. Yet the Fermi paradox demands bold thinking. If white holes do exist, even as fleeting quantum phenomena, their potential applications would redefine what's possible for an advanced society. Maybe the reason we're alone in the universe isn't that life is rare, but that everyone else has moved beyond methods we can even perceive. As we ponder this, another question arises. Could white holes alter our understanding of time itself? That's where our journey takes us next, into the mind-bending realm where white holes and the arrow of time collide. Now, let's take a step into one of the most perplexing realms of physics, the nature of time itself. White holes don't just challenge our ideas about space and energy. They might also twist our understanding of time's arrow, the one-way flow from past to future that we take for granted. To grasp how white holes could disrupt this, we first need to revisit entropy, the measure of disorder in the universe. Entropy is why ice melts in your drink but never spontaneously refreezes, why eggs scramble but never unscramble themselves. It's the reason time feels like it moves forward, not backward. Black holes are entropy powerhouses, swallowing matter and increasing disorder, but white holes, they're the cosmic rebels here. Instead of sucking in chaos, they spew out energy and matter in a way that seems to reverse the usual flow of entropy. If a black hole is a one-way street into disorder, a white hole could be a one-way street out of it, a cosmic rewind button. This idea gets even stranger when we consider time reversal symmetry. In Einstein's equations, time can technically run backward without breaking the rules of physics. Some theorists suggest that a white hole might just be a black hole playing the universe's tape in reverse. Picture a black hole forming, collapsing, and then bang, a white hole bursts forth, ejecting everything the black hole consumed. If this is true, then white holes aren't just objects in space. They're moments where time flips its script. What does this mean for the fate of the universe? If white holes truly reverse entropy, they could hint at a cosmos where the arrow of time isn't fixed. Imagine pockets of the universe where time flows differently, where entropy decreases instead of increases. It sounds like science fiction, but it's a serious possibility in the math. Some models even suggest that white holes could be seeds for new universes, birthing regions where time and physical laws operate unlike anything we know. Now, here's the catch. If white holes can reverse entropy locally, do they violate the second law of thermodynamics, which states that entropy always increases? Not necessarily. The universe might balance the books. White holes could offset black holes, keeping overall entropy on track while allowing bizarre exceptions. Think of it like a forest fire burning trees, but then new saplings sprouting in the ashes. The total disorder still grows, but not in a straight line. This brings us to the grandest question of all. Could white holes hint at a cyclical universe? If black holes crunch matter into singularities and white holes bang them back out, maybe the Big Bang itself was a white hole event, a reset button for reality. It's a dizzying thought, one that ties white holes not just to the birth of our universe, but to endless cycles of creation and destruction. As we wrestle with these ideas, we're reminded that white holes aren't just cosmic oddities, they're keys to unlocking the deepest mysteries of time, entropy, and existence itself. And with that, we turn to the next frontier, how scientists are racing to find evidence of these elusive objects, and what their discoveries could mean for all of us. Now, let's shift gears and peer into the future, where science and technology could finally bring white holes out of the realm of theory and into observable reality. The hunt for these cosmic enigmas is heating up, thanks to cutting-edge telescopes and missions designed to probe the universe's deepest secrets. But why is finding white holes so difficult, and what tools might crack the case? First, consider the Laser Interferometer Space Antenna, or LISA. Slated for launch in the 2030s, this space-based gravitational wave observatory could be a game-changer. Unlike its Earth-bound counterparts, LISA will detect low-frequency ripples in spacetime, the kind that might be produced by colossal events like merging black holes or, just maybe, the explosive birth of a white hole. If a white hole truly is a time-reversed black hole, its violent outburst could send gravitational waves echoing across the cosmos, leaving a signature LISA might catch. Then there's the James Webb Space Telescope, already revolutionizing astronomy with its infrared eyes. While JWST wasn't built to hunt white holes directly, its ability to spot unusual cosmic explosions like sudden, high-energy bursts with no clear origin could hint at white hole activity. Imagine JWST detecting a mysterious flare of radiation in an otherwise empty patch of sky. Could that be a white hole briefly flickering into existence before vanishing? It's a long shot, but in science, even the unexpected can lead to breakthroughs. But here's the catch: funding for white hole research is notoriously scarce. Why, for starters, white holes remain purely theoretical, with no direct evidence they exist. Grant committees often prioritize projects with clearer paths to discovery, like black hole studies or exoplanet searches. Plus, white holes challenge so many established ideas about time, entropy, and causality that some scientists dismiss them as mathematical curiosities rather than serious targets for observation. Yet the lack of funding hasn't stopped bold thinkers from pushing forward. Some propose repurposing existing instruments, like gamma-ray telescopes, to scan for white hole candidates. Others argue that upcoming radio telescope arrays, such as the Square Kilometre Array, might pick up strange, short-lived signals matching white hole predictions. And let's not forget quantum gravity experiments here on Earth. If white holes are linked to quantum phenomena, labs studying tiny space-time fluctuations could stumble upon clues without even looking for them. The irony is delicious. White holes, if real, could redefine our understanding of the universe, but proving they exist requires tools and funding that are currently just out of reach. It's a classic chicken and egg problem in science. Without evidence, funding stays low, but without funding, evidence is hard to come by. So what's next? The answer lies in patience and persistence. As technology advances and our cosmic maps grow more detailed, the chances of spotting a white hole or ruling them out entirely improve. Every unexplained burst of energy, every odd gravitational wave signal, brings us closer to solving one of physics' greatest riddles, and who knows, the key to unlocking white holes might already be hiding in data we've yet to analyze. As we stand on the brink of these discoveries, remember this: the universe has a way of surprising us when we least expect it, whether through a eureka, a moment in a lab, or an accidental observation in deep space. The truth about white holes is out there waiting to be found. As we wrap up this cosmic adventure, let's take a moment to reflect on the mind-bending journey we've just taken through the mysteries of white holes. From their origins as mathematical curiosities in Einstein's equations to their tantalizing potential as gateways to new universes, white holes challenge everything we think we know about space, time, and reality itself. They're the ultimate what-if of modern physics, a theory so audacious it blurs the line between science and science fiction. Think about it. If white holes exist, they could rewrite the story of our universe. Picture the Big Bang not as a one-time event, but as a white hole erupting into existence. Imagine black holes and white holes as two sides of the same cosmic coin, connected by wormholes or even time, reversed versions of each other. These ideas aren't just wild speculation, they're grounded in serious math and the boldest theories physics has to offer. Yet, for all their elegance, white holes remain elusive, hiding just beyond the edge of our telescopes and detectors. That's the beauty of science at the frontier. Some of the most revolutionary discoveries start as glimmers in the dark, ideas so strange they're dismissed as fantasy until the evidence catches up. White holes might be the next chapter in that story, or they might fade into the footnotes of physics history. Either way, the quest to understand them pushes us to ask bigger questions, build better tools, and rethink the very fabric of reality. So what do you think? Could white holes be out there, waiting to be found, or are they cosmic mirages, beautiful but impossible? Maybe you've seen them pop up in your favorite sci-fi, like the surreal white hole in Interstellar, or the time-bending twists of Doctor Who. Drop your theories, questions, or favorite white hole moments in the comments below. Let's keep the conversation going, because the universe's greatest mysteries are always more fun when we explore them together. And if you've enjoyed this deep dive into the unknown, don't forget to hit that like button and subscribe. There's so much more cosmic weirdness to uncover, from quantum foam to multiverses, and I'd love to have you along for the ride. Until next time, keep looking up and wondering what's out there.